This is a recording done by Dr. AJJ Mouton from Tshwane University of Technology. I'm going to explain to you sensors, how a sensor output is amplified and how it's then connected to an ADC. So the first thing I'm going to do is I'm going to connect a temperature sensor called the LM35, as that's a very nice type of sensor that you can work with, and it will explain a lot of things further. Now the data from this LM35 temperature sensor, I got that from, if you can look at the bottom here, this is the link. It's a Texas Instruments website where I got this data from. What's important to me first of all is the features. If I can go to this feature here, it says it's calibrated directly in Celsius, degrees Celsius, and it's a linear type of sensor. And as you can see here, it says this thing is 10 millivolt per degree Celsius. Now what this means is if you've got 100 degrees Celsius, that means the output of this device will be 1 volt. Alternatively, let's say you've got 50 degrees Celsius. That means that your output of this specific sensor will be 0.5. Like it says, this thing is a linear type of device, which is extremely nice. Now, this specific LM35 temperature sensor, as you can see here, comes in different packages. There's the TO can, which you can see here, which is a metal type of device. A TO92, which is this one, which looks similar to a normal transistor. This is the SOIC, which is a type of IC. When you see NC, that means not connected. And as you can see, it's got a plus 5 volt, it's got a ground pin and a V out. Same as the rest, only 3 pins being used. And then lastly, you've also got this type of package, which is the TO220 on the right hand side here, which looks like a voltage regulator type of package. So these are the different types that you can get it in. I myself, I'm used to this specific TO92 package, but it doesn't matter which one you use. This is the symbol or a sketch of the LM35, and as you can see, it's got a plus Vs voltage between 4 volt and 20 volt, and normally in our applications we will connect it to 5 volt. It's also got a ground pin, and then of course it's got the output pin, which is an indication of your temperature. And as I said before, for instance, if you've got a temperature of 10 degrees Celsius, 10 times 10 is 100 millivolt or 0.1 volt. That will be the output at this device. This, as you can see here, the maximum voltage is around about 150 degrees Celsius, which is quite, it will be useful for normal everyday use. What I'm going to do in this presentation, I'm just going to substitute this for the one on the right hand side, just showing you this is a temperature sensor, and that temperature sensor has got a certain output voltage, which will be used further in the presentation now. Now I have directed you previously to another presentation which explained this specific non-inverting amplifier. From that session you could basically saw that the gain, which is the voltage out divided by the voltage in, is 1 plus RF divided by R1. So what one would normally do here is maybe choose R1 or maybe choose RF, and then work out what the other value would be. So if I take R1, I basically select R1, then RF can be calculated depending on the gain. So why would we put this thing in this non-inverting amplifier? As I've said, in this specific case, if the temperature is 100 degrees Celsius, then the output would be a maximum of 1 volt. When I'm going to explain to you the ADCs, we would normally like this maximum output here to be around 5 volt, and this is why I would like to incorporate a non-inverting amplifier. And this is why I directed you to look at what is happening. How does this specific non-inverting amplifier working? So normally if I would, for instance, decide but my temperature range should be between 0 degrees Celsius and let's say 50 degrees Celsius, then the maximum output here out of the sensor, which would be the input to the non-inverting amplifier, would be 0.5 volt. Now it would be ridiculous to connect 0.5 volt to an ADC if your ADC maximum input should be around about 5 volt. So what we would rather then do is take this non-inverting amplifier and amplify the signal of 0.5 volt, and so that I can get out of here 5 volt, which is a better input to the ADC. So this is why I'm going to use this specific non-inverting amplifier. Let's look at an example now. I've got this temperature sensor sitting here, and as I've said previously, the temperature range is from 0 to 150 degrees Celsius. But what if I don't want to make use of this temperature range up to 150 degrees Celsius and only want to measure a temperature, let's say in a classroom, of between, well, let's say 0 and 60 degrees Celsius. So the temperature range I want to use this for, this temperature sensor, is then from 0 to 60 degrees Celsius. If there is a 60 degrees Celsius present on this specific sensor, the output of the sensor will be 0.6 volts, which is also the V-in of the non-inverting amplifier. So what we need to do is we need to calculate this amplification factor here, what it should be, in order to get an output V out of 5 volt. So if it's 0.6 on V-in, I want to get an output of 5 volt, which is the one that will be connected to my ADC, which I will explain in the slides to follow. So let's start off here. We say the temperature range is a maximum of 60 degrees Celsius. As I've said already, the sensor output will be 0.6 volts, which is also the V-in input on this plus input of the amplifier. So your V out must be 5 volt, and then we can easily calculate what the gain will be. The gain is the voltage out divided by the voltage in, which is 5 volt divided by the 0.6, which gives us this 8.33. And this is because the voltage and voltage cancels out. And we've also seen previously that the gain is this 1 plus RF divided by R1. So we've got the gain now, 8.33, so the unknown values will be RF and R1. And as I've said in my previous slide, you'll have to choose one value. Let's say we choose R1 to be a 1 kilo ohm resistance. If we do that, we can manipulate the formula to calculate RF, so which means that RF will be the gain minus 1 multiplied by R1. And because we've got the value of R1 now, we can then calculate, and we will get to a value of RF being 7.33 kilo ohm, which will be the specific resistance sitting here. Well, I know we don't get a 7.33 kilo ohm resistance, so what you can do in RF, in the place of RF, you can put a variable resistance of, let's say, 10 kilo ohm, adjust that resistance down to 7.33 kilo ohm, and once you've got that, you've got an amplification factor here of 8.33 perfectly. So just to recap, if I've got 60 degrees Celsius, it will give me a 0.6 volts on V-in, and it will give me a V out of a value of 5 volts. Similarly, if I've got a temperature of 30 degrees Celsius on the temperature sensor, it will give a 0.3, which is half of what the maximum is, and we will also get half out of what the maximum will be, which will then be 2.5 volt. So according to the temperature, we'll get a voltage out at VO, which is the one going into the ADC, and that voltage out here will represent a temperature. But I want to point out again, 60 degrees Celsius will give out a voltage of 5 volt. 30 degrees Celsius will give out a voltage of 2.5 volt. And these voltages represent these temperatures. And at some point we will do some calculations and we'll make some changes where we can see that I will bring back the value from your ADC where it is specifically showing the exact temperature, but we'll get to that stage when I do ADCs. Now in our classes I make use of an 8-bit ADC, and specifically the 0804, which is an analog to digital converter. So as it says here, an analog value is changed into an 8-bit value. So what will happen is a voltage can be placed on an analog, an ADC, a voltage in at V in, there will be a voltage, and according to the voltage, the output from here B1 to B8 you will get a binary value there, which can also be seen as a decimal value. So this decimal value that you get here is basically representing V in. So I'll explain that on the next slide, but basically what happens is Vref here is plus 5 volt, and that means that the maximum input that you can put on V in is 5 volt. And if you put 5 volt there, you'll have all outputs being a 1, which is 255 if I have 8 outputs. I'll explain it further in the next slide. In this specific, we've got a pin here called Vref, which is the voltage reference, which is this one here. I have connected here plus 5 volt. And what this means is that the maximum input voltage on V in can only be up to 5 volt. So it can be anywhere between 0 and 5 volt. If I put 0 volt here, all my output pins will be all zeros. If I put 5 volt here, my output pins will all be ones. So if it's all ones sitting here, I'll have a count here of 255. You get some ADCs which has got maybe, let's say, 10 output pins, which means that the maximum count will then be 1023. But for our purposes, for now, we're just going to work with an 8-bit. In exams, it can be up to 10 or 12, depending. And the voltage reference in exams can also be changing, of course. And the voltage input will basically change according to what this maximum voltage is here. I am making use of the 0804 ADC, and you'll see on our green development board that we did not connect Vref to anything. If you do not connect Vref to anything on that specific device, it means that the reference voltage is 5 volt. This is just a generic type of ADC, and this is why I have connected a plus 5 volt to see this, to say this is the maximum voltage. So the maximum voltage in is equal to the Vref, which is plus 5 volt in this case. If you should connect, let's say 5.5 volt on V in, it doesn't matter. You can only get to a maximum value still. If it's an 8-bit output, you'll only get up to a maximum of 255. So if you put 5.5 volt, you'll get 255. If you put 6 volt on V in, you'll still get 255, irrespective, because the maximum where it will do calculations up to, or changes up to, is up to 255 if it's an 8-bit output. So the maximum count is determined by the number of output pins, in this case 8, so n will be 8, so 2 to the power 8 minus 1 gives you the 255. If it's 2 to the power 10, it will be 1024 minus the 1, that's why I got it previously to the value of 1023. The next concept I'd like to explain to you is the step voltage. Now, what the step voltage means is, what is the increment, what should be the increment at V in to get an output change on the digital or the binary output pins. So if I've got 0 voltage here in, your binary output or the decimal output will all be zeros. So the question is, what should the voltage increase with at the V in to produce an output here of 1? And the way to calculate that is basically to take V reference, the reference voltage that you've got, and you divide that by the maximum count. Now we've seen previously that this maximum count here is 255 if all the outputs are equal to a 1. So so it's Vref divided by 2 to the power n minus 1, which gives us an answer of 19.61 millivolt. Now what that means is if I put 19.61 millivolt on V in, the output, if it was 0 and I put 19.61 millivolt in on the V in, the output will become a 1. In other words, if I put, let's say, 20 millivolt on V in, we will still have an output of 1 because we must increment twice 19.61 times 2 to get an output here of 2. So that is the concept of a V step, the step voltage, which basically means then if I've got the step voltage of 19.61 millivolt and I put 5 volt here, we know that it's going to be 255 here. So I can basically then generate a formula here where it says the decimal output is equal to V in divided by V step. For instance, if it's 5 volt in, maximum voltage, divided by 19.61, you'll get a value here of 255. And whatever voltage you put in, if you put, let's assume we've gotten a V in half of 5 volt, which is 2.5 volt, divided by 19.61 millivolt, you'll get a decimal output of around about 127 or 128, which is half of 255. So that's the concept of V step, the step voltage. So I can easily determine, if I know what the voltage in is, I can determine what will the output be once I've got Vref. Or I can also basically say, if I've got the output value, the decimal output value, and I know what Vref is, which means I also know what V step is, I can easily determine what V in is. So let's do a calculation here. Let's say the question is, if the input voltage V in is 3.7 volts, this one here, what is the decimal value out of this ADC? So we've got this formula now where we said the decimal output is equal to V in divided by the step voltage, which is 3.7, as we've said, that's the input voltage, divided by 19.61 millivolts, which gives us an answer of 188.67, which is close to 188. So the output decimal value will be 188 if the input voltage V in is equal to, the V in voltage is equal to 3.7 volt. And in this way we can actually calculate any output. Once we've got V step, I can calculate any decimal output value once I've got the V in voltage. Now let's look at a second scenario. So if, let's say question 2 here says, if the decimal output value is 204, this is what we find on the output pins. And the question is then, what is the input voltage, the input V in into the ADC? So we can easily calculate that because we've got this formula that says the decimal output value is equal to V in divided by V step. So if I now want to calculate what V in is, it will be the decimal output multiplied by V step, which is this 204 divided by 19.6 millivolts, which gives us an input voltage of around about 4 volts. So there again is a direct correlation between the, not a direct correlation, but there's a correlation between the voltage in and the output value in decimal format. So let us now connect all three components together, which is the temperature sensor, the amplifier, temperature sensor, amplifier, and also the ADC. And let's work through an example to see with a certain temperature on the temperature sensor, what will be the output of the ADC. So let's assume the temperature, the ambient temperature, is 25 degrees Celsius. That means I need to multiply that by 10 millivolt per degree Celsius, which gives us an answer of 250 millivolt or 0.25 volts. That will be the input voltage to this amplifier here. And we've seen from the previous slides that the gain, another way to describe that is AV. The gain of this amplifier is 8.33. That's what we've calculated before, because we said the maximum temperature on the temperature sensor will be 60 degrees Celsius. So with 25 degrees Celsius, with this amplification factor, I will get an output voltage out of the amplifier of 2.083 volts, which is then fed into this V-in, the input pin of the analog pin of the analog to digital converter. And if I now make use of my formula that I've described previously, we will take this 2.083 volts and divide that by the reference voltage of 19.61 millivolt, and that will give us an answer of 106. So what we've got here, we started off with an analog value of 25 degrees Celsius, and eventually we've ended up with a decimal value of 106. So what this 106, as you can see, 106, and there's 25, and of course these two looks totally different, but what we can say to each other is that this 106 is definitely representing 25 degrees Celsius. In the same way, if there was 60 degrees Celsius on this temperature sensor, I would have got, if I worked everything out, I would have got a 0.6 volt here. We know that I'll get on V out here from the amplifier a 5 volt, which will then give me a 255. So in that case, 60 degrees Celsius on the temperature sensor will actually produce a 255. And in both cases, the 106 I've mentioned now, 106 is representing 25 degrees Celsius, and if it was 60 degrees Celsius at the temperature sensor, it would have been represented by 255. So now I've actually got a value on the output of this, on this output binary lines here. I've got a number which is related to the temperature, the analog temperature in this specific case. And all I need to do now is to convert this number to what the real analog value is. Now on this next slide, I would like to explain to you what a scaling factor is. Now, we've already seen previously that this 60 degrees Celsius, I've done the calculations throughout, and it's represented by a number of 255. But you will not convince anybody that this 255 actually represents 60 degrees Celsius, especially if you show this to the guy on the street. So what we have to do is this number that you get out of the ADC converter, although this will be stored in a register in your microcontroller, we need to convert this to actually go to 60 degrees Celsius. So it's actually quite easy. All we have to do is we have to take this value and we have to multiply it as I've written down here. Your maximum output must be multiplied by this with a scaling factor, and that will give you the real temperature. In other words, I'll have to take 255 and I'll have to multiply it with a certain factor, which will then give me 60, and this 60 will then be stored in another register inside your microcontroller, and that's the one that I will display then. In other words, if I display 60, that is the real temperature. So it's quite easy then to determine that the scaling factor, as you can see it there, if I do manipulation here, the scaling factor is 60 divided by 255, and that gives me an answer of 0.2353. So in other words, if I take this 0.2353 and I multiply it by 255, I will get a value of 60, which is the real temperature. So I've now converted the number that I've got here to the real analog value. And in the same way, whatever I get here, whatever value I receive here, if I multiply that by 0.2353, I will then get the real analog value. Let's look at the next slide. In our example, we have calculated that if my ambient temperature is 25 degrees Celsius, it will actually give us a value of 106. Well, normally you will not know what the temperature is, and so if you measure this and you get a value of 106, you need to know what is the real temperature, because you've only got this value here once you connect all of these components together. So if I take this output value, in this case I said here output value multiplied by the scaling factor is equal to the real temperature. In the previous slide I just used the maximum output value and the maximum real temperature, but this will also apply here. So in this specific case I want to calculate what is the real temperature. If I've got a value of 106 here, So the real temperature is 106 multiplied by the scaling factor, and that works out exactly to be 25 degrees Celsius. So whatever value I get here on the binary output of this ADC, although it represents the real temperature, it is also, all I need to do is multiply this output value, the decimal output value, with a value of 0.2353 in this specific case, and that will give you the real temperature, and that's the temperature that you will use in further calculations and further displays, etc. If you have any questions regarding the sensors, amplification and the ADC, you can email me at motonajj@tut.ac.za. Thank you.